Yeah, good morning. So I would like to thank Samruddhi and the other colleagues around for organizing this wonderful series of um, StatMake meeting. I come from Jodhpur, which is a beautiful place. I invite you to visit in the right season. Today I will be talking to you about our recent work on ion transport mechanisms in liquid electrolytes, which have applications in battery technologies. This work was recently accepted a days ago in this paper. So I would like to recall what happens to Brownian particles when it is immersed in a fluid and how the relationship is going to be there between diffusion coefficient and the viscosity. So they are inversely proportional to each other. That's what I wanted to highlight. Sometimes people interpret this viscosity effects through something called as the underlying relaxation phenomena. Here I'm denoting that as tau c. So you can imagine diffusion coefficient in fluids to scale as 1 over tau c. You can eventually think of in the language of conductivity and assume that of course conductivity is inversely proportional to viscosity or some relaxation phenomena and some consequences for battery technologies which I will not talk about here, but otherwise let us go to the what is literature. In electrolytes community in 2015 Magin and co-workers have done a series of electrolytes, liquid electrolytes, and then they have shown yeah, conductivity. This is actually non-Einstein conductivity where diffusion coefficient is directly proportional to this conductivity. So the ionic conductivity is proportional to one of the underlying relaxation phenomena. Here it is ion pair relaxation time scale. Yeah, so the inverse scaling you can notice 1 over tau c is the x-axis. And after that, we have in a series of papers also demonstrated such a relationship between diffusion coefficient and a particular relaxation phenomena in a variety of electrolytes. So here it is a blend electrolyte. The previous one was for neat, that means pure ionic liquid electrolytes. And here we are trying to show for blend liquid and a polymer electrolyte. Similar behavior exists. And also some synthetic polymer electrolyte plus ionic liquid electrolyte, which means a ternary electrolyte, in which also you have similar relaxation dictating the diffusion coefficient of ionic species and some neat polymerized version of electrolytes, that means polymer electrolytes, pure polymer electrolytes, in which also you have such a behavior. So the point I'm trying to make here is that the diffusion coefficient or the ion transport mechanisms in a variety of liquid electrolytes and polymer electrolytes is directly correlated to a certain relaxation phenomenon. So that's what I wanted to recall. So in this talk, what I'm trying to focus on is we want to ask at a given constant temperature how salt induces changes in viscosity and how salt induces changes in whatever the identified, so-called identified relaxation phenomena, and how these viscosity and tau c, or the relaxation phenomena, are correlated to conductivity. Not at limited range of concentration, but across a wide variety of a wide spectrum of concentration. That's what is our question. And also, you can see here from the literature, there exists some explanation of ionic conductivity across a broad spectrum of concentration through something called as this equation, which I'll come back to in a while. We also want to see whether we can improve such a explanation, such an interpretation of ionic conductivity as a function of concentration. So what we did was all atom MD simulation wherein the intra and intermolecular interactions were modeled through a classical force field. And then we perform MD simulation used within the framework of linear response theory, some equilibrium approach or the non-equilibrium approach to calculate all these quantities that I just mentioned. So let me go to directly the results. We have diffusion coefficient which goes down with the salt concentration, but conductivity goes up and down. Eventually, at high salt concentration, conductivity goes down completely. So it looks like from other analyses like density or the viscosity or the relaxation phenomena, it looks like the the exponential decay of diffusion coefficient can be explained by qualitatively, of course, but actually, when you look at the quantitative scaling relations, they are not. So there is some deviation from the power law of Stokes-Einstein, whatever dictated by, right, for the diffusion coefficient. Now, when we look at the tau c or eta viscosity, we can see that they do exponentially increase, but only at a high concentration. At low concentration, you could see that the changes are not that much noticeable. So for that reason, if you look at viscosity and tau c, there is no one-to-one correspondence between them. In fact, if you dig in little bit deeply, we notice that only at high concentrations, there is a one-to-one correspondence between viscosity and the tau c, but at low concentration, we have this particular relationship. So which means we can think of what could be the implication for my conductivity now, ionic conductivity. So when I calculated ionic conductivity and plotted against eta, we see that at high concentration, yes, this can be explained as if within the framework of whatever Stokes-Einstein like power law, but at low concentration, no. So what happens at low concentration? So the conductivity that comes in an electrolyte at low concentration is simply the presence of how many number of, that means what is the concentration of ionic species. So in the literature, that what I showed, typically it was assumed that it's proportional to C, but we are introducing here an exponent which to take care of or to account for the whatever the marginally low, but the presence of ion-ion correlations at low concentration. And at high concentration, we have just now seen, of course, viscosity goes 1 by eta, which means we also saw eta goes to exponentially increasing. So which means conductivity goes exponential minus C. So now by combining these two effects, we proposed a little bit of modified version of the existing unified equation, C to the power alpha times exponential minus C, which explains the conductivity over a broad range of concentrations satisfactorily. We also applied these ideas into a newly emerging electrolyte, sodium-based polymer electrolytes. This is completely polymer electrolyte, and we still find a nice fit with the simulation data using this C to the power alpha exponent kind of improvement. So I would like to conclude by summarizing this here, and I would like to thank my group, particularly Hema, Shipra, and other students around for contributing to this research. So I would like to take any questions that you have or suggestions.
Questions? So I have a question. So
yeah,
when you change tau c, what do you exactly change in the experimental system to change this tau c?
So here, concentration is the one that will induce changes in tau c. But
I saw a slide where you had different plots for different concentration.
Right.
You had a plot for diffusion constant versus tau c
so
for different concentration.
that data was, a particular data point in that plot was taken for a given salt concentration. So these are all independent simulations. Every data point is a different salt concentration in that sense.
Yes.
But you can have other parameters in the system which can induce changes in all these physical quantities.
If there are no more questions, let us thank Santosh once more.
Thank you.